At this point, we've been using two different sets of I/O libraries. We've today started talking about file descriptors, represented by int, and the system call API of open, read, write, and so on. Meanwhile, we've been using printf, and printf and those kind of functions are part of standard C. In that world, file handles are represented as file pointers, capital F-I-L-E star, and the relevant calls are fopen, fread, fwrite. They start out pretty similar, but with slightly different APIs, and standard C has a lot more stuff in it. There is a bridge between these. So standard C is the portable one. So you can use this API on Windows too, where the operating system provides different primitives, different system calls. But when you're running on Unix, of course, the way that standard C library is implemented is by using the Unix system calls. And there's also a function fdopen, which explicitly bridges the two worlds. So if you have a file descriptor at the Unix level, you can turn it into a file star at the standard C level using fdopen. And there's our certain predefined files, standard in, standard out, standard error, provided by the standard C I/O library, that are initialized by using fdopen on those three file descriptors, 0, 1, and 2, input and read mode, of course, and output and error in write mode. Let's look at a comparison between these two things. So these two programs do the same thing. Create a pipe, fork, the child process writes hello a bunch of times, a million times, and the read side reads hello a million times. So that is the Unix API version. We'll call that uio.c. And on the standard C library side, very similar. Create the pipes, then we turn that pipe into a file star using fdopen and use fwrite to write a million hellos. And similarly on the read side, we will read a million of them through the C API using fread. Okay, so let's call that cio.c. And we can compile both of them. So Unix IO, let's see, I have to give them different names. And CIO. So both of these should do the same thing. UIO prints out that it did 5 million characters. CIO prints out that it did 5 million characters. You may have noticed that the CIO went faster. That's not just an artifact of the video. If we time them, then we see CIO takes 0.1, 0.2 seconds, whereas UIO takes much longer. Now, why would that be, given that we know the C library is using the system calls underneath? Turns out that the C library is about 10 times faster. So why the difference? Well, let's suppose we're using Unix IO. Then we use the CSApp wrapper, capital read, but that just turns into a lowercase read with error handling. And that means that 5 bytes are read by asking the kernel to read those 5 bytes from the pipe. And so that means that we're performing a system call through the kernel every time we ask for 5 bytes. And that transition from user code to kernel code turns out to be more expensive than just calling a function in user code. If we use the C library, we ask for 5 bytes. The way things are typically set up, it doesn't actually ask the kernel to read from the pipe just 5 bytes. Instead, it asks for a whole bunch of bytes at once, usually something like 4K. And then it'll put the amount of those that you didn't ask for as the user code. It'll just put them in a buffer. So we only used up 5 bytes of the 496 that were gotten, up to 496 that were gotten from the kernel. In this case, since we had 5 million bytes, we could easily get 4K of them. So that when we do another fread on 5 bytes, then it doesn't have to go to the kernel, it just copies more of those bytes out of its buffer. So the C library is using the system call functions to implement I/O, but it also introduces a layer of buffering. It's similar on the right side when we do write with system call. CSApp turns into a system call, and so it's asking the kernel to put 5 bytes into the pipe every single time going through the kernel. Whereas with the C library, when we write 5 bytes, it'll says, okay, I got those 5 bytes. It'll store it in the file record, and as long as there's space available to store it. Eventually, when you write enough 5 bytes, then it will have a bunch of them. Can't actually be 4096 because that's not a multiple of 5, but something like that. When it gets to some large number of bytes, then it flushes the buffer that's in the file pointer. This should say writes, not fwrite. Flushes those bytes by asking the kernel to actually write them. You can also request this even if you haven't used up all the buffer space. There is a C library function called fflush that says, please go ahead and write them out to the file. Maybe it's because it's a pipe and you want the other end to definitely have seen it at that point. Maybe it's because you're writing to a file and you want the bytes actually on disk at that point before you carry on. So that's why flush is available.